All right. I think it's time to get started this session. Um, this is the parallel session 12A for cosmology. So please make sure you are in the right room. Um, so, uh, so we're happy to have the speakers this session. The first speaker, could you share, Mark? Could you share your?
Yep.
Yes. All right. So before starting, I must mention that each slot includes 15 minutes for talk and 3 minutes for Q&A session, and then 2 minutes for to set up next talk. So please make sure your time is still remaining. So first speaker is Mark Hartsberg from Tufts University. He will be telling us about the causal structure of superfluid dark matter. Please start.
Okay, so thank you very much to the organizers for this very nice conference. Okay, so this talk is based on this paper done with Jacob Litterer and Neil Shah, who are graduate students here at Tufts University. So first of all, as we all know, there has been tremendous success of cold dark matter on large scale. And this comes from CMB, large scale structure, baryon acoustic oscillations, Lyman alpha forest, galaxy clustering, and altogether paints for a kind of consistent concordance model where these pieces fit together very well on these large scales. However, some authors have suggested that there are possible difficulties with cold dark matter on the galactic scales. And in particular, I will focus on the baryonic Tully-Fisher relation, relating the observed baryonic mass of a galaxy to the asymptotic rotation velocity VF. And one can see a host of galaxies sitting here with relatively little scatter around a scaling relation mass proportional to velocity to the 4. On the other hand, at least in simplified treatments of cold dark matter, the relation appears to be more like mass proportional to V cubed. And so there is some discrepancy here. Now, whether this is a true discrepancy that requires us to modify cold dark matter is still an open question, but it has added some motivation to think that we might be missing something on the galactic scale. Now, in this direction, some authors have went in a radical direction to try to modify gravity on galactic scales, or so-called MOND. So let's say if instead of the regular Newton's law, that acceleration is proportional to mass over r squared, if instead, following Milgram, one says that the acceleration is proportional to the square root of this, then by setting the centripetal acceleration to v squared over r, the factors of r cancel, which leads to very little scatter. And then indeed, when one gets the relation one desires, that mass is proportional to v to the 4, recovering the baryonic Tully-Fisher relation. So perhaps we should be just modifying gravity somehow on galactic scales. However, implementing this in a consistent theoretical framework is known to be notoriously difficult. For one thing, we have a theorem, which is that the unique causal Lorentz invariant theory of massless spin-2 particles at large distances is just general relativity. So from this point of view, all we could do is add higher dimension operators, which would be irrelevant on the galactic scale. Nevertheless, there is something we can do. We can add new degrees of freedom, namely scalars, which, if they are sufficiently light, could mediate a new long-range interaction, although they would need to have some kind of peculiar interactions to mediate this new funny scaling relation. So is this possible? So to set our bearings, let me mention a kind of simplistic attempt in this direction. So suppose we add to the standard model some new scalar phi. which may or may not also be the dark matter, some scalar. And its dynamics is governed by some function f, which is a function of x, defined as this Lorentz invariant kinetic term. And f may also depend on phi itself. And suppose this function f has two different asymptotic regimes. So first of all, imagine when x is small, which is relevant to low densities or large cosmological scales, f is just the standard x. So in other words, you have a canonical scalar, which can be quantized in the standard way. However, imagine as you go to large x, which is relevant to higher densities, more relevant as you go into the galactic scales, that f deviates from this linear shape and instead enters an x root x or 3/2 scaling regime. Okay, now, to be clear, one can dream up functions that have these asymptotic relations. Here's just an example of a function that does that. And just to emphasize that by going to large field values, one can indeed stay within the regime of the effective field theory, even though this secondary term can somehow dominate over the first term. And that's because if the field value is large, nevertheless, the particle energies can remain low. Now, this type of scaling relation here can be useful because if you write down the corresponding classical equation of motion in the static limit, you obtain this modified Poisson equation with a source here coming from this term, where phi is coupled to the baryons, let's say through the trace of the energy momentum tensor of the baryons. So if you then solve this modified Poisson equation, you obtain that the acceleration between the baryons is indeed the form one desires, namely this square root m over r squared, precisely the scaling one needs in order to reproduce the baryonic Tully-Fisher relation. Now, there are two basic problems with this approach. One is theoretical. So if you have this type of 3/2 scaling, then one can show that high energy perturbations on top of this Mondian solution are in fact superluminal. And I'll come back to related details later. But the other is phenomenological. So although this scalar becomes canonical at large scales, where the function f reduces to the familiar linear relation, that doesn't mean that the force completely disappears. It then would mediate a more regular, albeit fifth force, 1 over r squared. So to illustrate this, if we look at, say, acceleration versus radius r, this here would be the standard Newtonian 1 over r squared force law. This new field phi is mediating some new 1 over r force law, which is giving the desired Mondian dynamics here. But then as you go to even larger scales, it just relaxes to a kind of 1 over r squared fifth force, which means it can compromise the success of cold dark matter on large scales and general relativity. So what we would really like is some framework that carries the best of both worlds. So on the one hand, we would like that on large scales, we just have a massive scalar that can just obtain the success of cold dark matter. But on the galactic scale, some light degree of freedom becomes active and can mediate a Mondian-like force. And one can achieve this using spontaneous symmetry breaking. And this was done in this very nice work by Bereziani and Curie from a few years ago. And so their idea was essentially to promote this real scalar phi to a complex scalar capital phi, whose dynamics is organized by some global U1 symmetry. And I'll write the corresponding kinetic term x like this. Now, as an example, imagine this function f, essentially the Lagrangian for this scalar, has this form. So this term here is the canonical Lagrangian for a massive scalar, and so it will reproduce cold dark matter on large scales. But then there's this other term, which has these sort of peculiar scalings here, including x plus m squared phi squared all cubed. And this term will become more important as we go to larger densities to galactic scales. And it turns out this allows for a phase transition to a superfluid on the relevant galactic densities. But furthermore, if one decomposes phi in terms of the modulus rho and phase theta, then in the superfluid phase, one has, of course, spontaneously broken the global U1 symmetry, and the massless Goldstone theta, the phase, can then act as a long-range force mediator. In more detail, having factorized out the rapidly varying e to the IMT, we have a slowly varying phase theta and modulus rho that can describe this superfluid condensate. It's useful to decompose X in this way in terms of rho, and the Goldstone theta gets packaged in terms of this function that I'll call Y as follows. At tree level, you can integrate out the heavy modulus or Higgs mode rho as follows. And then one finds that the low energy effective action just for the Goldstone theta is in fact this form. It has exactly the y square root y, or desired 3/2 scaling. And so by coupling to baryons, this can indeed mediate, the Goldstone can mediate the desired Mond-like force, and hence reproduce the baryonic Tully-Fisher relation on galactic scales. But moreover, as we deviate from the superfluid regime on large scales, we go back to the normal phase in which we only have a massive scalar. And so that massive scalar can then give rise to the success of cold dark matter on large scales without any additional fifth force. So this all looks very promising. In this work, we wanted to put these ideas to some theoretical consistency tests. So let's suppose you decompose the complex phi in terms of its real and imaginary parts, phi 1 and phi 2. And let's consider high energy perturbations around this superfluid background. And the perturbations I'll call epsilon. So I'll be interested in kind of relativistic perturbations. One can write down the linear equation of motion for these high energy perturbations. So it's an equation where you only track the two derivative terms acting on epsilon. And its coefficient here is governed by derivatives of f with respect to x. And a reminder that f is this sort of peculiar looking function here. Now, you have a pair of coupled modes here associated with the fact you have a complex scalar. And you can readily diagonalize this system. First of all, you find that the Goldstone, the perturbation in the Goldstone direction is regular, but the perturbation in the Higgs direction is non-standard. And in fact, it obeys a kind of modified wave equation of this form, where this capital G mu nu plays the role of an effective metric, and it has this form. So if this effective metric is strange in some way, it could potentially compromise the causal propagation of these perturbations. And so that's something that we'd like to analyze in detail. So first of all, to have any regular wave propagation, you need to ensure that the metric governing this has eigenvalues that are Lorentzian, namely negative plus plus plus. And that, ensuring that, is also well known as so-called hyperbolicity of the wave equation. So in order for that to be true, one can check that, first of all, this coefficient f prime has to be positive. And then a second condition for hyperbolicity is that there is some combination of terms here, which turns out to be f prime plus 2x f double prime, also has to be positive for hyperbolicity of the wave equation. If you have wave propagation, then you should further check that the signal speeds are subluminal, and that leads to this inequality that one needs to satisfy. So this connects back to various old work on this topic. And here it's just generalized to the case of a complex scalar organized by a global U1 symmetry. And so we'd like to test these consistency conditions in this case of the superfluid dark matter model, which we did in this work. So first of all, one finds that the first hyperbolicity condition is always obeyed. However, the second hyperbolicity condition, B, turns out to be proportional to Y. And in the Mondian regime, Y is in fact definitively negative. And so that means that B is negative and the second hyperbolicity condition is broken. Now, since the background primarily depends on time through the e to the imt factor of the superfluid phase, this is a breaking in the temporal direction, which is a kind of ghost-like mode, albeit it's not a Lorentz invariant mode because the background obviously breaks the Lorentz symmetry. Now, once you've broken hyperbolicity, you can no longer really talk about the speed of propagation of modes. However, if you move away from the true Mondian regime and go kind of to an intermediate regime halfway between Mond on galactic scales and CDM on large scales, you can maintain hyperbolicity, but then one finds that there are regimes of phase space in which superluminality takes place. So this can be a problem too. Now, in this work, we went further and said, okay, let's consider the most general form of Lagrangians of this form. So you can write down a whole tower of operators like this, where every term has this funny scaling. There's a power of n upstairs and 3n downstairs. And this scaling here ensures that you achieve the desired 3/2 scaling in the effective theory for the Mondian dynamics. And the whole freedom comes in these coefficients G sub n. If you choose G sub 0 to be positive, you will recover cold dark matter on large scales, and then the higher G sub n's control the galactic dynamics. But regardless of what you choose, we were able to prove a general theorem is that whenever the Gn allow you to enter a Mondian regime, the second hyperbolicity condition is in fact always broken. And it's a breaking in the temporal direction that's ghost-like as usual. And again, if you go away from the Mondian regime to some intermediate regime, you can find parts of phase space that are superluminal. So to conclude, superfluid dark matter is a novel way, perhaps the only known way, to obtain both the success of cold dark matter on large scales and the success of Mond on galactic scales. And further, this is done in a unified framework. In this work, we studied a general class of models and proved that high energy perturbations on the superfluid background always violate hyperbolicity. It was in the temporal direction, so ghost-like behavior in this Mondian regime. And furthermore, intermediate regimes can exhibit forms of superluminality. I didn't have time to discuss it, but there are problems in related models too. So this leads to an open question, which is there any other model out there which is free of these theoretical problems that can be constructed? Or alternatively, one can ask, can one rigorously show that we don't really need to do this and that cold dark matter itself can reliably reproduce the baryonic Tully-Fisher relation and other observed galactic properties? Okay, thank you for your attention.
Thank you. So now it's Q&A session, but it's almost running out of time, and we're gonna have just a few quick questions if you have. So if you have any questions, please raise your hand or type your question on a chat.
So can I have just a quick question?
Oh yes, please.
So the superluminality might be, you might mention, but the superluminality might be inconsistent with positivity, so-called positivity bound. But do you mean that, so this is the problem?
This superluminality would mean it's superluminal in the usual sense. This would not have any standard Lorentz invariant UV completion. But that's right. So it should furthermore violate one of these inequalities on the scattering amplitude.
Okay.
But I want, so that is indeed already a problem with the sort of what I call the simplistic approach, which has phenomenological problems. But what at least I found surprising in this work was that we also found that when you're in the Mond regime, you've even worse, you break hyperbolicity as well. So it's an even stronger breakdown that even the simplistic approach, even worse in some sense.
All right, so time's up. So let's thank the speaker again. And let's move on to the next speaker. Could you share? Yes.
Do you see my screen?
Yes. So the next speaker is Kohei Kamada from Tokyo University. He will be talking about WASH in leptogenesis as a new physics framework for baryogenesis. So please start.
Okay. So first of all, I would like to thank the organizers for giving me this opportunity to talk here. So today I'll talk about WASH in leptogenesis. So this is a kind of, so it is not a new model, I would say, but this is a kind of new framework for baryogenesis. So this talk is based on the work with Barry Donke and Kai Schmitz at CERN, and Kyohei Mukaida, who was at CERN, but he recently moved to KK, and Masaki Yamada, who seems to be in the audience. Okay, so let me proceed. So my talk is on baryogenesis. And yeah, we have already had several talks on baryogenesis, and we had also a good public talk by Professor Hitoshi Murayama yesterday about for the baryogenesis, or why we don't have antimatter around here, or why we have very tiny but non-zero baryon asymmetry of the universe. And in 1967, the Sakharov proposed the condition for generating baryon asymmetry of the universe, now known as well-known Sakharov's condition. That is B violation, CNCB violation, and deviation from thermal equilibrium. And I guess it is not so difficult, I would say, implementing this effect in the model of high energy physics, because if we extend the standard model so that we introduce heavy particle and it decays sometime in a B violating as a CNCB violating way, then we can satisfy these Sakharov's conditions simultaneously very easily. And indeed, we know that the grand unified theory provides us a good candidate for such a baryogenesis model. And it has been explored in late 1970s, very old one. I would say, yeah, it is a very well motivated model. And so in that sense, we have understood the origin of the matter-antimatter asymmetry of the universe if we have grand unified theory. But yeah, of course, it is difficult to prove it experimentally. People might have thought something like that. However, finally, people note that the story is not so simple. This is one way that the gut baryogenesis might suffer from monopole of production. But more importantly, at a later time, electroweak Farallon noticed. Electroweak Farallon is a non-perturbative process that changes to the B number and lepton number simultaneously. And so due to the non-trivial vacuum structure of the non-Abelian gauge theories, we can have the effective potential with respect to the Chern-Simons number, so that we have such a potential. And then, the Shapovalov pointed out that at high temperature, the Farallon process is very effective, so that if we have primordial B plus L asymmetry, that the Farallon would wash out the baryon asymmetry, this B plus L asymmetry. And yeah, this is the schematic picture of such a process. So that the surround baryogenesis generates the baryon asymmetry in a B minus L non-breaking way. Then surround with washout will wash out the baryon asymmetry. So in that sense, so the SU5 simple SU5 got baryogenesis has been killed. Then the option shown thus far is to generate B minus L asymmetry much before electric symmetry breaking, or generate B plus L asymmetry after electric symmetry breaking. This is the electric baryogenesis, and this is the leptogenesis. So yeah, first option, this one needs to violate B minus L asymmetry. No, B minus L symmetry. And the B minus, but the B minus L symmetry is an exact non-anomalous symmetry of the standard model. So in that sense, we might not be so happy if we violate B minus L. But nevertheless, we had a good candidate violating the lepton symmetry, B minus L symmetry, that is right-handed neutron mass. Due to right-handed neutron mass term, immediately lepton number is violated. This means B minus L is violated. In such a way, so if we produce lepton symmetry in this direction, then Farrell washout in this direction, so we have the baryon symmetry. So we are happy. But the problem is that such a baryon asymmetry generation mechanism from the right-handed decay needs severe constraint conditions for the CB violation at the right-handed mass. Then here I would like to address another issue on that. So the point is that all people might think that all the B plus L generation mechanism before electric symmetry breaking might not work as a baryogenesis mechanism that is responsible for our universe. But it is not really the case I would like to comment. The point is that electric sphareron washout of B plus L asymmetry by electric sphareron complete only when the electron U-curve gets equilibrium and the temperature is around the less than 100 TB. So at a higher temperature, electron U-curve interaction is not in equilibrium. So it gives us another symmetry, the conserved charge. And so in that sense, and similar thing would happen in other U-curve interaction. So that means, so at lower temperature, the standard model has only B over 3 over lepton charge as a global conserved charges. But at higher temperatures, so this is the figure from the Barry and her collaborators. But the electron U-curve is in equilibrium in this temperature, up, down, strange, muon, charm, bottom, tau, electric weak sphareron are in equilibrium at somehow higher temperatures. So this means that we can approximate the temperature regime like this, so that it might be stopped. You might not see my screen sharing. So
yeah, I think it's stopping.
It might be good for me to turn to the so let me change. This. So you see my screen?
Yeah.
Okay. So what I'd like to say is that So what I'd like to say is that there are several temperature regimes that the U-curve interactions are in equilibrium. So in that sense, at the temperature regime, we have several other conserved charges. So at the lower temperature, we have B over 3 over Li minus plus the electron, right-handed electron asymmetry. And at the higher temperature, we have several other conserved quantities. So this means that at the B plus L genesis or asymmetric genesis, that would be erased by electric sphareron, and the completion of the washout has some time duration. So in that sense, something can be implemented before before the completion or after generation of the asymmetry, before the completion of washout, the generation. And so let me clarify what is going on. So once the initial asymmetry is generated by a genesis mechanism, one can determine the conserved charges and evolution of each particular asymmetry, how it redistributes in an Turner-Harvey way, so that we have the chemical equilibrium condition for the interaction as well as the Farallon condition here. And from this, we can write down the equation for each chemical potential can be written as the chemical potential for the conserved charges. And if we have some approximate conserved charge mu alpha, such as baryon asymmetry or B plus L asymmetry, that might not be conserved, then we can write mu alpha as a function of the complete conserved quantity here, like these quantities. So from this calculation, we have this well-known formula for the mu B asymmetry and baryon asymmetry in terms of the initial B minus L asymmetry. But this equates only when after electron gets in equilibrium. Then, something can be different once we introduce right-handed neutrinos. And I explained what is going on. So once we introduce the right-handed neutrinos, we have another equilibrium condition for the interaction of right-handed. I'm considering the type 1 system mechanism. So that we have the interaction for right-handed neutrinos, so that we have such a equilibrium condition for the right-handed neutrino. At the present, this just determines the chemical potential for the right-handed neutrinos, so that it does not change anything. However, once the temperature going down, then the temperature reaches at the right-handed neutron mass. At this time, the mass term of right-handed neutrino in a lepton vibrating way is very effective. And then this interaction makes mu and chemical potential for right-handed neutrino to be 0. Then at this point, in this way, the B over 3 over Li charge is no longer conserved charge, and it will be distributed. And by requiring this mu NR to be 0, or this term to be 0, one can rewrite the previous equation. Oh, sorry. This equation to be in this way. So the mu alpha plus mu H is here, but it should be 0. And this quantity is written in terms of mu C, the exact conserved quantity, and the B over 3 over Li asymmetry. So that we have the B over 3 over Li asymmetry is in terms of the other conserved quantity. Then we see that B minus L asymmetry is in the system. And in this process, the lepton asymmetry, with the help of electric Farallon, lepton asymmetry is not washed. B minus L, B plus L asymmetry is not washed, but washed in. So we name this process as washing process. And so as I said, there are several temperature regimes where the conserved quantities are different, so that we can have such a recipe to evaluate the value, the B plus B over 3 over Li asymmetry like this. So if we have the non-zero chemical potential here for them, then we can just multiply these parameters. Then we get the asymmetry for the delta here. And here is how the baryon asymmetry is redistributed. I mean so the fan at the higher temperature larger than the right-hand neutron asymmetry is generated, and when the Yuka interaction equilibration, then the redistribution happens. And when here, and when the right-hand neutron is going down, and when the right-hand neutron gets the temperature goes right-hand neutron mass, the washing process happens, if the relevant charges survives, then the lepton asymmetry, B minus asymmetry is generated like this. But the right-hand neutrino becomes very massive quickly and it disappears quickly. But the other asymmetry, in such a point, B minus L asymmetry gets a good concept quantity again. Then the temperature just becomes the less than 10 to 5th GeV. Then the electronic equilibration, then the usual, well-known redistribution of baryon asymmetry. So that I quickly explained the advantage of Washing leptogenesis. So what we did is that we disentangled the Taurus condition two parts. So at the high temperatures, we have C and CP violation and deviation of thermal equilibrium. So that an asymmetry generated, but it doesn't have to be B minus L. And the B minus L violation is implemented in the right-hand neutrino at a lower temperature. So we disentangled it. And the C and CP violation is not required right-hand neutrino sector. And depending on the initial asymmetry Washing works relatively light right-hand neutrino mass, so that it could be consistent with naturalness and the consistent with so-called neutrino option. In the case of the baryon leptogenesis, it cannot be reconciled, but now it is possible. And the application, the SU5 gut baryogenesis could be rescued in this way. And another possibility is that axion inflation. In the case of axion inflation, the helical hyperengaged field can be generated, and at the same time, the baryon asymmetry is generated with respect to chiral anomaly equation. But such an anomaly, so the magnetic helicity, hypermagnetic helicity and B plus L asymmetry is generated in the same way, so that it could be annihilated at some time later. But before the annihilation of the B plus L asymmetry and the hypermagnetic helicity happens, if washing process happens, then the completion of the cancellation does not occur, so the axion inflation can provide us the good baryon asymmetry for the impact. Yeah, so this is related to the work, the talk by Fumio Uchida yesterday. So if you are interested, you can also look at it, his talk yesterday on YouTube. Okay, so this is in the summary. So the washing process, we provide a new framework for baryogenesis. So if we have a new baryogenesis mechanism that does not produce B minus L at a high temperature, but the right-hand neutrino and with washing process can help your model. So this is our proposal. That is. Thank you very much for listening.
Thank you. So now it's time for question and some comments. If you have any questions, please raise your hand or text in the chat or just speak out.
No questions?
No questions.
Oh, it's a shame.
Okay, so I had a question about, it's a bit unclear to me what is the difference from the conventional thermal leptogenesis, because once we have a right-hand neutrinos, then it automatically generates lepton symmetry. But so the framework looks the same as you have talked.
Yeah, so I would say that the point is that C and CP violation is not required on right-hand neutrinos. So in thermal leptogenesis, we need the CP violation in the right-hand neutrinos. But the right-hand CP violation is implemented in the initial asymmetrogenesis mechanism. So this is the difference. So at the time of the asymmetric generation, C and CP violation is implemented in this mechanism. But the right-hand neutrino sector does not require C and CP violation here in this sector. So this is the complete difference. And in that sense, we could say, even if we do not see any CP violation in the neutrino sector, it is possible so that it makes the model zombie. So it might so it is hard to rule out this mechanism. So so for the thermal leptogenesis, if we have the complete experiment, so that determines the CP violation in the neutrino sector, then we can tell if the leptogenesis can work or not. But in this case, the C and CP violation is put it to the other sector. So yeah, in that sense, it's a bit so. So this mechanism is hard to rule out. This might not. This is a good point, but as also experimental in an experimental point of view, it is a bad point.
Mm-hmm.
Is it okay for other question?
Yeah. Mm-hmm. I see. Yeah. Thank you. I think the time is up, and okay. So thank you for the interest talk.
So
let's move on to the next.
To leave. So okay, back.
Oh yeah. Yeah. All right. Thank you. So could you share? Yes. All right. So the next speaker is Kohei Fujikura from Tokyo. He'll tell us about ectoweak like baryogenesis with nuclear matter. Please start.
Yeah, thank you very much for the introductions, and thank you very much for giving me an opportunity to have this talk. So, could you see my cursors? Is it okay?
Oh, I don't think.
Oh, okay. Anyway, okay, it's okay. Okay. So my name is Kohei Fujikura. I'm a member of the Rescues in the University of Tokyo. This work is in collaborations with these authors, Keisuke Harigaya, Rokuan Wans, and Yuichiro Nakai. So let us begin. So what I would like to talk today is baryon symmetry of the universe, BAUs. So we know that after the inflations and before the Big Bang nucleon synthesis, tiny but non-zero baryon symmetry must be generated by some mechanism, so-called the baryogenesis. Here, NB is a baryon number density and S is the cosmic entropy density. So to generate the baryon symmetry of the universe, Saharos pointed out that 3 conditions must be fulfilled, satisfied. The first one is the baryon number violations, because if we do not break the baryon number, we cannot generate baryons. The second condition is the CP violations, because if there is no CP violations, baryons and same amount of the anti-baryon is generated. So essentially, there is no baryon symmetries. So finally, out of thermal equilibrium process is cleared. Otherwise, the generated baryon symmetry is washed out by the plasma effect. So a long time ago, these authors pointed out that it might be possible to generate or describe the baryon symmetry universe within the standard model framework in the following way. So the first condition of the baryon number violations is satisfied by the Spartanon process, so which is the non-parallel thermal effect, which breaks the B plus violations. And second, the CP violations. If you look into the standard Lagrangian sectors, we have one CP violating phase for the weak sector, so-called the Kabibo-Kobayashi-Maslow phase. And finally, out of thermal equilibrium process can be realized when the electric phase transition is of strong first order, in which inside the bubble, Spartanon process is decoupled. So unfortunately, but it turned out that electric baryogenesis in the standard model framework cannot be realized by the following 2 reasons, not one reason. So first of all, so the strength of the CP violations only from the CKM phase is insufficient, as pointed out by those authors, because so the naive estimations or conventional wisdom told us this kind of order estimation. So here, DCP is the characterize the strength of the CP violation of the standard model sectors, so which is the combinations of the Giles-Cook invariants. So here, J, Giles-Cook invariant parameterize the mixing of the weak sectors, especially for the Yukawa sectors. And also, this CP violation phase, CKM phase, can be eliminated when pair of the up-type or down-type Cook masses are degenerated. So since we have additional degrees of freedom, which can be, which make CP violation effects vanish. So naively, we can naively expect that this mass square difference, Cook mass difference, parameterize the strength of the DCP, I mean the CP violation effect. So since our final result, baryon symmetry normalized by the cosmic entropy is a dimensionless quantity. So this DCP is a dimension from quantity, so must be divided by some relevant energy scale of the baryogenesis mechanism. So in the electric baryogenesis mechanism, it might be the critical temperatures. So if we divide it, critical temperature of the phase transition, it turned out that this NB over cosmic baryon symmetry is much, much smaller than the observed value due to the fact that quark mass or quark Yukawa coupling is so tiny. In addition to the insufficient CKM phase, with the observed Higgs mass, it turned out by the lattice simulation, I mean, the rigorous calculations show that electric phase transition is not of the strong fast order. I mean, the electric phase transition is of crossover behavior. So here I would like to say that in the electric baryogenesis in the standard model cannot be realized due to the two facts, insufficient CP violation effect and the we cannot realize the out of the thermal equilibrium process. So this implies that, okay, so if you would like to generate a baryon symmetry universe by the first order phase, especially for the electric baryogenesis mechanisms, you may need to introduce an additional CP violations. Also, you need to make the electric phase transition is of a strong first order. However, as I said, in usual model, a usual electric baryogenesis model, the CP violation, additional CP violations is introduced around the scale of the electric scale because the electric phase transition is over electric scale physics. So such kind of additional CP violation is stringently constrained by the precision measurements, especially for the electric dipole moment measurement. So then it is natural to ask a question that how do we generate the observed baryon symmetry universe by electric baryogenesis, which is consistent with the EDM measurement. So for these motivations, we consider the electric-like baryogenesis scenario where we do not consider the electric phase transition from here. So we consider extension of the standard model with SU3 colors times SU2 additional chiral gauge symmetry right-handed times SU2 left-handed sectors times additional UX charges. So this symmetry is spontaneously broken to the standard model gauge symmetries. So this implies that, we introduce additional gauge symmetry breaking. So there's association with the phase transition. So if this if this SU2 times UX to the hypercharge, which is broken to the hypercharge phase transition is of first order and can generate B minus L symmetry by additional SU2 Spartan process, we can satisfy the first condition of the Sakharov's condition. So we can generate the baryon symmetry. We can generate a baryon symmetry different from the electric phase transition. So here the generated B minus L symmetry is transferred by the SU2 Spartan process. So it turned out that the breaking scale of the SU2 times U1x to the U1y hypercharge phase transition, which is I would like to call the new phase transition, is around the tentative scale by the Collider experiment. So from now on, I'd like to explain these statements more precisely. So first of all, I'd like to explain the model. So Higgs sector is given by this one. So GLR is our full gauge symmetry and GSM is a standard gauge symmetry. GLR breaks to the GSM via the Higgs wave given by HR, which belongs to the fundamental representations of the additional SU2 gauge symmetries. So this implies that this HR is the order parameter of the new phase transitions. And in this model, a standard model like Higgs can be identified with the HL or the large phi, which belongs to the bifundamental representations of the SU2 and SU2R. So let us explain the quark sectors and the lepton sector. So here I show the quarks and the lepton sector of our model. So Qi and Li denotes the standard quark sectors and the left-handed sectors and left-handed lepton sectors. And also, since we extend our gauge symmetry to the SU2 times the SU2R, which is only couples to the right-handed particles, so we can embed it like a Q bar I and L bar I, which is the right-handed quarks and the right-handed leptons. But in these minimal extensions, you can see that so there is a symmetry under the there's a symmetry under the exchanging of the left and right symmetry. So this implies that in this minimal extensions, B minus L is not broken by the SSR chiral anomalies. So this implies that B minus L is not generated by the SSR span. Only the B plus L is generated. So in this case, we cannot generate, we need additional chiral fermions to violate the B minus L to succeed our strategy. So for this reason, we introduce a new leptons in the following way, borrowed from these papers. We introduce 3 generations of the new leptons, L bar I, the EI, and LI. So this new fermions has 3 generation behaviors, and the Yukawa coupling between the HR and new leptons are completely same to the quark sector in the standard model Higgs sector. So we have one CP binding phase, so called the CKM phase in the new lepton sector, which can be the source of the generation of the baryons. But in this chiral extensions, you may worry about the we need to avoid the cancellation of the chiral gauge anomaly, not the global anomaly. So to do so, to cancel the gauge anomaly, we introduce the additional new leptons, L Childers and Y bar and chi bar, from as shown in the this gauge charge assignment. So then our theory is anomaly free, but at present setup, you can see that the L bar EJ and these new leptons possesses own lepton number. So once we can generate these new leptons asymmetry by the first order phase transition, we cannot convert these asymmetry to the standard model leptons or the barrier symmetry. So we need a portal coupling. I mean, we need a coupling between new leptons and the quarks or our leptons, standard model leptons. So these gauge assignments, it turns out a portal coupling between the new leptons and standard leptons can be written in the renormalizable interactions given by this purple shaded lines. So thanks to this portal coupling, E and N asymmetries are transferred into the standard model lepton symmetry. So at this present setup, I may explain the our model, I mean the new particles or so on. So from now on, I'd like to explain how our model can generate the B minus L asymmetry by the wall dynamics and how the generated B minus L asymmetry can transfer to the standard model lepton symmetry, barrier symmetry. So first of all, first order phase transition proceeds through bubbling equations. And as I said, now we are interested in the case, we are interested in the phase transition associated with the new chiral gauge symmetry breaking, where the order parameter is given by the HR, new Higgs. So in our paper, we investigated a parameter space which leads to this first order phase transition. But in this talk, due to time limitations, so please assume that I took the parameter space where the first order phase transition takes place. So once the bubble nucleation realized, the bubble eventually coalesce with each other and leads to the completion of the phase transitions. And during the bubble expansions, what happens is that in the in front of the wall, since inside the bubble, HR is condensate, so which occurs waves. So from the Yukawa coupling, these new leptons becomes massive, while the outside of the bubble, new leptons is massless. So from the outside of the bubble, see the bubble wall as a quantum mechanical barrier because it's inside, new leptons becomes massive. So we have some quantum mechanical scattering process, and during this scattering process, reflection coefficients of new leptons and the antiparticles can be defined. I mean, which is sourced by the 3 generations of the CKM phase in the new lepton sectors. So finally, B minus L can be generated if the SSR Swannon process is decoupled in the Bloch phase. And we also, here, I assume that I take this parameter space where the Swannon decoupled conditions is satisfied. So from now on, I'd like to explain how generated E or N lepton asymmetries can be transferred to the standard lepton or barrier symmetry. So generated LNA asymmetry by the moving bubble wall. Okay, once this LNA asymmetry is generated, then the outside of the bubble, SSR Swannon process converts a part of the LNA asymmetry into the standard model V plus L and ellipsion chi asymmetries. Okay. Then, as long as the portal coupling is efficient, so that the new leptons and standard leptons are in thermal equilibrium, Then these asymmetries, I mean LNE asymmetry, epsilon chi asymmetries are transferred to the standard leptons and baryon symmetry by the ordinary CCS Farinov process. So this corresponds from this step to this step. So LNE epsilon chi has some non-zero symmetry, but thanks to the portal coupling and SCS Farinov process, we have a non-zero lepton and baryon. So finally, after the completion of the phase transition, these particles becomes massive, eventually decay into the standard model leptons. Then we, as long as if the ordinary Farinov process is efficient, we have a conversion of the P plus L asymmetry. So as I said, the CP violation effect is completely similar to the standard model sector. So I can use a conventional wisdom. I mean, we can order estimate the amount of the baryon symmetry in our model. So here, J prime is a gyroscope invariant in our new lepton sectors, and YE and YN is a Yukawa coupling of new lepton sector. So rephrase this baryon symmetry normalized cosmic entropy can be realized 10 to 11 or 10 to minus 10 when we take large Yukawa couplings around the order 0.1 and a slightly larger gyroscope invariant. So this implies that a large Yukawa coupling can generate or observe the baryon symmetry in the universe different from the our electroweak baryogenesis within the standard model framework. So this is a rigorous result in our model. So we took some benchmark point where the SC2 gauge coupling and also the Higgs self couplings. And it turned out that this figure shows that, indicate that, so indeed, large Yukawa couplings can generate or observe the barriers in the universe. And the right panel shows that the third generation of the Yukawa couplings and also the SC2 gauge coupling, new gauge coupling. So I would like to slightly comment on the phenomenology in our model. So we have a collider constraint since the new gauge boson Z prime and W plus minus R are produced, can be produced by the colliders and decay into the pairs of standard fermions. So from the LHC, we have a constraint like this kind of way. So this pink colors and the sky blue regions is already excluded. So the wave of the VR must bounded below around the 15 temps. So this is the reason why I state we have a lower bound of the breaking scale. And we clarify some of the parameter space where the fine tunings are required and so on the stability of the Higgs potentials. So this is a summary. So electric baryogenesis needs an additional CP violation, which is stringently constrained by the EDM measurement. So we consider first order phase transition associated with new chiral gauge symmetry breaking occurring at around the 10th scale by the LHC constraints. And our model can produce the observed baryon symmetry. So yes, that's all. So thank you very much for your attention.
Thank you for nice talk. Now it's time for questions. If you have questions, please raise your hand or text in the chat. No. Okay. I had a question about
Yes.
the decay of the newly introduced leptons, because it's nevertheless it looks like
Yes.
no ordinary right-handed neutrinos, for instance, the N
Yes.
or chi,
Yes.
and it
Yes.
eventually decays into standard model particles.
Yes, exactly.
Producing lepton asymmetry.
Yes.
On top of the contribution for the fast space transition, fast order phase transition. Is it negligible, or is it already took into account your result?
You mean that you worry about the decay of the right-handed neutrinos?
Producing lepton asymmetry as well, on top of the already generated by phase transition at the time of the phase transition.
Yes. We include, at least we include, we calculate the final baryon symmetry of the universe, including all of the effects generated by the lepton symmetry, LNE and L epsilon chi, generated by the first order phase transition. Yes.
And such a CP phase is also contribute to the electron EDM, I think. Is that possible?
Yes. So okay. So as I said, we may have some of the aspects. So yeah. So as I said, the EDM measurement stringently constrained our usual model. in our model, we also have a CP violation. So there may have a, how to say, EDM bounds. But as we know that, how to say, the source of the CP violation is a seeking phase in the new lepton sector, which needs to be three, how to say, all of the new leptons must be involved in the loop process. So which appears as a higher order, and we need a chirality fix, which can be provided by the electron mass insertion. So which is much smaller than the present bound, as long as the expectation value of the VR is larger than the 15 tail. Yeah. So this is a kind of the subdominant constraint in our model.
I see.
Yeah.
All right. Thank you. So now it's time to move on. Let's thank the speaker again. Okay. So let's move on to the next talk. All right. Yes. So next speaker. Well,
sorry. Right.
Are you right?
Yeah. Yes. Did you see my screen?
Yeah. Now I see your screen.
Okay.
All right. So the next speaker is Min-Si He from Tokyo University. He will be talking about reheating in a mixed Higgs and R-square inflation model. Please start.
Okay. Thank you for the introduction and the opportunity for me to give a talk here. And today my topic is the reheating in the mixed Higgs R-square model based on these three papers. So this is the plan of my talk. And first I will give a brief introduction about this model, and then I will talk about the first stage of preheating, tachyon preheating, and the late time perturbative preheating reheating in this model, and finally give a brief summary. And so what is the mixed Higgs R-square model? So it's quite simple. So it's just a simple addition of the R-square, the Stravinsky model and the Higgs inflation model. This is the Lagrangian given in the Jordan frame with a non-minimal coupling between the Higgs and the gravity, the scalar mass m, and the self-coupling of Higgs lambda. And here the convention is conformal coupling corresponds to the -1/6, and we focus on positive Z. Okay. And so why do we consider this model? So as we know, the Stravinsky model and the Higgs inflation can give very observationally favored predictions on this NSR plane, say in the central region. And this is the first motivation of this model. However, there are many other important reasons to consider this model. For example, the Higgs field. This two-field model can serve as a UV extension of the Higgs inflation, because as intensively studied in many papers, the Higgs inflation is not UV completed. The cutoff scale is much lower than the Planck scale, especially during reheating. And this will cause some problem. For example, when the Higgs field oscillates during reheating, every time the Higgs field crosses the origin, it induces a very large spike in the effective mass of the longitudinal mode of the gauge bosons. And this spike, the scale of this spike is larger than the low cutoff scale of the Higgs inflation. So so this is one important reason that we need a UV extension of this model. And also many studies focus on the origin of the R-squared term in the Higgs inflation, and also they also discuss in the presence of this R-squared term how the vacuum stability of the Higgs field can be improved. So I will not talk about these in detail, but there are very important motivations to consider this model. And okay, next I'm going to talk about my main topic, the reheating. So the reheating analysis actually can be done in either Jordan frame or Einstein frame, but here, due to the simplicity of the gravity sector in the Einstein frame, I will focus on the Einstein frame. So we define a new scalar field phi and use a conformal transformation to transform the Jordan frame action into the Einstein frame, where we have two scalar fields. One is phi, the other is the Higgs field. Of course, here, for simplicity, I take the Higgs field to be a real singly scalar. And there's a non-canonical coupling in the kinetism of the Higgs field, but this E minus alpha phi could be just approximated to be unity during reheating, because phi is very small in that period. And they have a complicated potential. The potential looks like this. So as you can see in the positive phi regime, there are two valleys. And these two valleys serve as the attractor for the inflation dynamics. So the slow roll inflation occurs in one of these valleys. And the dynamics can be described as a effective Starovsky model or effective Higgs inflation in the large Xi regime. So this is good because it means that the inflation predictions from these two field model actually coincides with its two single field limit. And as long as the parameters m, xi, lambda satisfy such a condition, this m tilde is the effective scalar mass, which is fixed by the amplitude of the curvature perturbation observed on CMB. And later, we will further fix the self-coupling of Higgs field, lambda, to be 0.01 for definiteness. Okay. So effectively, we have a one-dimensional parameter space. Looks like this. So we can talk about this model. By fixing lambda, we can talk about this model using Xi or M or a newly defined parameter theta that are equivalent. As you can see in this parameter space, we basically divide it into three regimes: the R-square-like regime with a Starobinsky limit here, and the Higgs-like regime. And within the Higgs-like regime, there's a small red region where it corresponds to the strongly coupled regime. Inside this regime, the perturbativity is not guaranteed. So we will stay out of this regime. As you can see, the Higgs limit actually corresponds to this point. So it is, from this point of view, it's very natural that the Higgs inflation actually suffers from strong coupling problem. Okay. And so after inflation, the inflaton field oscillate. For example, around here. This is generic for all the parameters. So for different parameters, the subsequent reheating process will be different. But this first stage is generic for all the parameters. The inflaton oscillates around here. And actually, this period corresponds to the zero crossing of the Higgs field in the single field Higgs inflation. So as you can imagine, since such a zero crossing point in the Higgs inflation now is expanded, become a finite with a finite width. So the large spike, which causes problems in the Higgs inflation, will be become mild, become weakened. So we can analytically and numerically show this point. And these are three examples of the spikes. These spikes. And the leftmost panels corresponds to the parameter at the boundary of the strongly coupled regime. So as long as we stay out of that regime, the strongest spike we can get is this one. As you can see, it's still very small, much smaller than the single field case. So in this sense, this spike cannot exceed the cutoff scale. Sorry, I forgot to mention that in this two-field model, the cutoff scale is lifted to the Planck scale, as shown in some reference I showed before. And now the spike scale is also lowered. So in this sense, the strong coupling issue will never appear as long as we stay outside the strongly coupled region shown in the parameter space. But however, since the spike is weakened, so as we can expect, the particle production induced by this non-adiabatic change of the effective mass will be kind of diminished. So it cannot have significant effect for the preheating or reheating. Then we need to consider other possibility. I mean, the subsequent evolution of the system. So after this generic first stage preheating, then there are two typical choices for the inflaton. To go. The one is to go up the hill in the middle, and the other is go back to the attractor, the valleys. So we'll talk about the first one first. This corresponds to the tachyonic preheating. As you can see in the Higgs direction, the curvature of this potential is negative. So the Higgs field will experience tachyonic instability. But we need to know when this will happen. So assume that we choose a model parameter which will, after the first stage, we'll go into one of the valley. Then we continuously increase or decrease the parameter. Then we expect that the trajectory will continuously changes from this 2 to 1 and to another 2. So in the middle case, we will realize the tachyonic preheating, which can be understand in this schematic picture. So horizontal axis is the model parameter, and the y-axis is the efficiency of the tachyonic preheating. So we expect that as we scan the parameter space, we got something like this. And yeah, and we can also numerically or analytically find out this the position of this highest point, which is shown in this figure. So they are separated into, classified into two branches. One is in the Higgs regime, Higgs-like regime. The other is in the R-square-like regime, the red one. And so with these parameters, the tachyonic preheating can be maximally realized. However, as you know, you can imagine that we need some fine tuning to get to these parameter points, right? And what if we deviate somewhat from these parameters? What will happen? So it's natural that the efficiency will decrease rapidly, because once the Higgs field fall to one of the values, the tachyonic preheating will be terminated. So we need to find out how much fine tuning we need. So we set a criterion here. So for example, we need such kind efficiency to realize effective enough preheating. Then we compare the width of this gradient band with the whole peak, and we define the degree of fine tuning. Then we find that in the Higgs-like regime, the black point, we can have relatively small degree of fine tuning to realize very efficient tachyonic preheating. However, in the R-square-like regime, we need very much fine tuning. This is natural because we don't expect any tachyonic preheating in the R-square inflation. So, yeah. And so in that case, we need to consider the non-fine-tuned case. Non-fine-tuned case where it means that the tachyon instability is not significant or it is completely absent. So what happened? In this case, the inflaton will go back to the valleys. One of the valleys, and have a small oscillation around it. So in this case, the perturbative decay of the scleron field and the Higgs field will occur, and they play an important role not only in determining the final reheating temperature, also maybe they will affect the scattering process between the produced particles by the tachyon instability and the background fields. But I will only talk about the first point here. And yeah, we can write down the decay rate of the scleron and the Higgs field. So the dominant channel for the scleron to decay is, of course, through the decay into the Higgs field, because we have a large nominal coupling like this. And one point need to mention is that this factor is very large in the positive scleron regime. So actually, this channel is basically kinematically forbidden throughout, for a long time, unless we get to really, really late time. But maybe before that time, the reheating already completed. Okay, and the decay for the Higgs field can decay into weak bosons or top quark to bottom quarks or something. But the most efficient one is the top quarks one. And during the negative scleron regime, the top is massless because the vacuum distribution value of the Higgs field is 0. So it can decay very efficiently to the top quarks. And then, yeah, and of course, not only these two channels, but the other Higgs decay into weak bosons should be considered in the numerical calculation. I just showed 2 examples. And also, yeah, and I considered 2 cases. One is in the presence of insufficient tachyon preheating, where we take the preheating process into account phenomenologically as some initial radiation in the system, which consists 90% of the total energy. And another case is the completely absent of the tachyon preheating, and we compare the result. So the first one with some initial radiation is plotted in the blue, and the no radiation is plotted in the black. As you can see, there's not significant difference between these 2 plots in terms of the reheating temperature. And also for more Higgs-like regime, of course, it is natural to expect that the reheating temperature is higher because the decay rate of the Higgs field is much larger than the scleron. Okay, and as the parameters get close to the R² limit, we expect that it approaches to the R² case, like 10 to 9 GeV something. And this red line is just for reference. The decay, the temperature of the calculated from the scleron decay rate with both channels open, which is not so realistic actually, especially for the lower one. Okay, yeah, this is on my talk, and yeah, I would say the mixed Higgs R² inflation is healthy up to the Planck scale, and give observationally favored predictions. And the first stage of preheating is not problematic as in the single field Higgs inflation case, but it's not efficient enough. So we need to consider the tachyon preheating and the perturbative reheating in the late time. Yeah. Thank you very much.
Right, thank you. Now it's time for questions. you can just raise your hand or ask in the chat. Oh, there's one from the audience. Maybe you can text.
I cannot see the text. So.
Oh. Let me see. So I think he cannot speak. Oh, no. What? Oh. Maybe a question from Takehiro Terada. Oh. No. I don't see him in there.
Hello. So I have a question about the inflation regime.
Okay.
I'm curious about the case of negative Higgs potential. It is obvious that if we are in the Higgs-dominated regime, then it's not viable. But in the case of curvature, the Stravinsky-like regime, if the Higgs potential is negative in the large field region, in that case, is inflation possible in this mixed model?
You mean the Higgs field is around the origin?
Higgs field, I'm assuming a situation that...
you mean negative?
Yeah, negative.
Negative
value.
Oh, you mean negative Higgs or negative phi? Sorry.
Higgs scalar potential, value of the scalar potential is negative for large Higgs value.
For large Higgs value?
Yeah.
It's not going to negative?
Yeah, but suppose.
So you mean if the self-coupling go to negative value?
Yes.
In
for,
that
for our
I don't consider that case here, but I think there's some paper consider such a case, and they discuss that about the PBH production or something. But here I only fix the lambda to be 0.01, and yeah, I'm not sure. How the inflation occurs in that regime. Sorry, but yeah, and also there's some study here. For example, they discuss the improvement of the vacuum instability of the Higgs field in the presence of R squared terms. So so this is all I know about the negative lambda case.
All right, thank you. So we are running out of time. So let's thank speaker again. And let's move on to the next speaker. Did you share? Oh, yes. Could you share your screen?
Okay, hi.
Yeah.
You should be able to see, right?
Yes. All right, yeah, we can see that. All right, so she's the last speaker this session. The next speaker is Adriana Minkara from Chunan University. She'll be talking about cosmology of linear Higgs sigma models with conformal invariance. So please start.
Okay, so first, thank you for giving me the chance to give this talk about my recent work with my advisor, Hyunmin Lee. I am a PhD student, and well, I'm gonna start my talk. first I'm gonna do a brief introduction that I think most of you will find easy. Then I will speak about how to recast Higgs inflation into a nonlinear sigma model. And then I will talk about our work, which is general linear sigma models and how to explain inflation and dark energy with them. And then I will wrap up and make a short conclusion. So this image is a very old picture of the universe in which we can see two things. The first is that the universe is pretty homogeneous. And the second is that there are tiny density fluctuations, temperature fluctuations that are correlated in the large scales. So the question is, why, if the universe was made of disclosed patches, how can they have communicated in the past? So Big Bang cosmology cannot explain that. And that is why we need inflation. Normally we think of inflation like slow rolling inflation, in which we have the inflaton field rolling down the potential until the moment in which the kinetic energy becomes very large. And then inflation ends. And after inflation, we have a period in which the inflaton starts oscillating and giving its energy to standard model particles. So inflation will provide a solution to the horizon problem, but it must last enough time, up to 50 to 60 e-folds, to explain the density perturbations that we see. So one of the most economic possibilities is to think that the Higgs standard model will be the inflaton. And this is the Lagrangian for Higgs inflation, in which we need a non-minimal coupling with gravity in order to explain the observations. And the problem is, as was pointed in the talk before by Mingxi, that this coupling is large, so it has a problem that it leads to unitarity violation. And to solve this unitarity violation, we need a UV completion. Then this can be done by adding a new scalar field to the system. Before moving on, I will explain what is a general linear sigma model, which is given by this Lagrangian. And in this case, this is the most general case, we can have a symmetry, ON symmetry. And if we minimize the potential, what we see is that the minimum is not in zero. So the length of this vector will be fixed, but the direction is arbitrary. To understand better what this means, we can reparameterize the fields. And then we realize that our Lagrangian has one massive sigma field and n-1 massless pi case, which we're used to think that are the pions or the Goldstone bosons. So our initial ON symmetry is broken to the ON-1 symmetry. Now, in the standard model, we have the Kira Lagrangian, in which we have the constraint pi squared plus sigma squared equal to the decay constant of the pion. And we have this constraint for sigma. Then we can rewrite the kinetic term like this. And here I just put the Kira Lagrangian kinetic terms and down the Higgs inflation kinetic terms, just for you to see that it is similar. And so this is what we'll be talking about. So in our case, Higgs fields will be our pseudo-Goldstone bosons. So now, how to understand Higgs inflation as a nonlinear sigma model? We start from our Higgs inflation Lagrangian, and we do a conformal transformation. So we introduce an unphysical degree of freedom, which is the conformal field. Now, after a few field redefinitions and adding the constraint equation, we see that we change the Lagrangian into something that doesn't have a non-minimal coupling, but instead it has a non-canonical kinetic term. And next thing we do is we fix the gauge, but by setting the Planck scale, and we rewrite Higgs inflation as a nonlinear sigma model with this Lagrangian subject to this constraint. So if we add this constraint as a Lagrange multiplier and we allow to have sigma like a dynamical field, then we will have a UV completion of the theory. Now, Starobinsky is just adding a R squared term to Higgs inflation. And we can do the same tricks, perform conformal transformation. In this case, this chi is giving you the constraint. And one important point, even if I didn't follow many details, is that we will get the same nonlinear schema model for Higgs inflation and for Starobinsky. And now all of this has been done. This was a review of previous works. Now we have any general curvature terms here where alpha will be giving you the order of the expansion. And in this case, the potential will be given in terms of this I, which will be our Lagrange multiplier. And we want to decouple sigma by minimizing the potential, giving you this constraint for the Lagrange multiplier, which will always have an extremum if k is bigger or equal than 1. So we started from this Lagrangian, which has some important point. Besides that, conformal invariance is visible in our approach. We also have only renormalizable terms as for the non-gravitational part of the theory concerns. So now our potential is given by this equation here. And we will go to the Einstein frame to study inflation by performing a Weil transformation, where omega is this conformal factor. So now we will integrate out the Higgs field because it will not affect during inflation. And we find our effective potential only in terms of the sigma field or the scalaron, like this. And we rewrite it in terms of a canonical field and find this final form, which is the form that we will use to study the inflationary predictions. So from this potential, we can derive the small role parameters, and we will be rewriting them in terms of the number of e-foldings. And here are our predictions for the spectral tilt and the scalar to tensor ratio. So first we will notice that we have 1/n² terms, and this will be different from Starobinsky or sigma inflation because we have Higgs quarting couplings in there. And also we have these extra terms, but they will not affect much. They will be small due to the fact that lambda is of the order of K1 psi, and then this will be small. This effect of the 1/n² can be testable in future measurements of the CMB experiments. And then another thing we did was to see how our reheating temperature changes due to the fact that the scalaron is also allowed to decay mainly to the Higgs boson. Now, if we include into our Lagrangian one extra term, any term with larger curvature, our potential becomes like this, which is exponentially suppressed in general, except for the case when P is equal to 1, when we have Starobinsky inflation. But the thing is that when P is larger than 1 or smaller than 0, our inflaton potential is exponentially suppressed. And then instead of explaining inflation, we can explain dark energy in the late universe. So here we made a plot of our potential for different values of n in the case in which Higgs is decoupled. Now to have a more deep discussion about dark energy, we consider this potential in just the form of an exponential. And we solved the Friedmann equation together with the scalar field equation. And then these two equations can be recasted as shown in this paper as these three equations where gamma is a factor given by the potential and its derivatives. So we plotted in these panels our solutions for two sets of initial conditions. And here, I will explain a little bit. We plotted the current observations and constraints and our solutions for three different values. We see that for n equal 3 and n equal 2, our solutions are in agreement with Planck data up to 1 sigma, but n equals to 1 can be different up to 2 sigma in tension. So also we see that the smaller our initial field value is, the more in agreement we are with observations. So in this side, I didn't say, but we have the equation of state versus time. And this in the right side, we have the evolution of the equation of state against time. So I think I went too fast. So in summary, our general sigma models with conformal invariance are a suitable UV completion for Higgs inflation. In particular, the family coming from R², these models will lead to successful inflation, which predictions that can be tested in future experiments. We have the possibility to include new terms, which will provide dark energy, and they have tracker behavior. And our results for dark energy are consistent with the experiments within 1 sigma for some values of n. Then we have future work, like for example, trying to generalize these corrections for the inflation predictions. So thank you so much.
Thank you. Now we have a time for question, about 4 minutes, I guess. If you have any questions, please raise your hand, or instead you can write. Okay. From Mincy, please.
So yeah, may I ask questions about the reheating? So what's the particular, specific mechanism, reheating mechanism in your model?
Mm-hmm. I think it's, I'm not sure if this is what you're asking, but we're considering instantaneous reheating.
So, sorry, what?
Because let me know. Because reheating, I started studying like not long ago, so.
Okay.
But I think it's instantaneous reheating, and the thing we just consider the decay of the Higgs to all the electroweak sector and the decaying of the sigma field to Higgs. So these are what is.
I see. Okay. Thank you.
Right. Any other questions? Oh, I see the questions in the chat, the Q&A session. I can read from Takahiro. Is a scalar sector of the theory still renormalizable in the presence of the higher curvature term? That's a question.
I think so, but I will say that I have to think about that because I don't want to lie, but I think it is.
All right. So
can I give a question?
Oh yes.
Yeah, one simple question is, in the presence of these higher curvature terms, do we still have the black potential at light field division? Just in my knowledge, we do only have the flat potential only for our scale. But I just.
But you're calculating the dual theory, and you're working with that. So, good question. Very good question. Maybe not. Maybe you're right. But then oh yeah, of course. Because here these terms are leading to dark energy, not inflation. And I think for dark energy, we don't need a flat potential.
I mean, so do we have successful inflation in the cases too?
In the case that we have larger curvature terms, we don't have inflation.
Okay.
At least that's how I understand. You can explain rather inflation or rather dark energy. So these terms will be for dark energy.
I see. So you do not want to solve the problems simultaneously. Right?
Yeah, exactly. It's not simultaneous.
I see. Yeah.
All right. Is there any questions? I had a quick questions about the dark energy. I thought the exponential type of potential has been excluded by BB and bound, but is there any way out in a particular case?
I mean, we consider BBN in our lines. They are containing BBN bounds. So I didn't know that this kind of potential was suppressed.
Well, if the if the such a scalar field has is going to the so-called scaling solution, normally such cases can be excluded. But yeah, maybe the US solution is not that case. That's why.
I'm actually gonna look for it. Thank you for the comment.
All right. I think now it's time to stop, and thank you for your interesting talk. So now we are going to end this session. So let's thank all of the wonderful speakers this session, and hope to see next session starting in 1 hour, I think. All right, thank you.